Yes, recording.
Yeah. So let's start with our first question, uh, which is like bitwise and numbers range. So we are given a range, and we okay, and your n the max limit is this. You have to return the bitwise end of all the numbers in this range, including the extreme points also, like 5 and 7. Yeah. So what like brute force would be like normal, right? Am I audible?
Yes, you are audible.
Okay.
Yeah. So brute force, the way you are saying will be uh, start with something from the starting input, go all the way
Yeah.
to the end, right? Okay. And then keep on adding each and every element in it.
At that point, yeah.
Yeah. So we could actually optimize that to a lot, right? Because we can do something in the, because it's like a bitwise adding, so we can
Yeah.
use some bitwise techniques here and then reduce that time complexity. Okay.
Yeah.
So so to look at this, one way I was saying, like if we had some number like from 2 to 10, right? In that case everything is going to be zero, right? If
Yeah.
my
Because yeah.
uh, sorry, what? Yeah, go ahead.
No, go ahead. I mean, you can convert the bit. You can annotate on the screen. Will be more.
Okay,
I
okay,
mean, for
just
visualizing the pattern. Yeah.
right, right.
Yeah.
Well, I was also just thinking loud. So in the sense, oh, so because this becomes slightly tricky, and so if this is 2 and if it is 10, right? So in this case, if I convert 2 also in my bit representation, it's going to be 1 0, right? Okay, and then if I do 1, sorry, if I do 10, it is going to be 1 0 1 0. Okay. So then if I start looking, I know that this bit is going to be 0 for sure. Okay. But all these bits are also going to be for 0, right?
Mm.
So now the question remains only of the this bit which is on 1. But if I see the distance between both of them is too huge, and I'm surely this bit, some of the number in between will have this bit also to be 0, right? And so it will also be added to 0. So my answer will be 0 in this case, correct?
Yeah.
So then I started thinking, like if I have something like this, when my input, the first input is very smaller than the the second input in the range, right? The left and the right. So I thought it will always be 0, but that's not the case, right?
Yeah.
But if it is very small, like 2, and then here in this case 10, or maybe after certain bits, then yeah, that might make sense. Yeah,
So
but
basically,
then
if there is a flip, then result will be made to 0, right?
yeah, so there might be some bit in in that range, it will make it to 0. But then if you look at the range, so you can have any number like this, a very some big number, and that also might be very large, right? So if you have
Yeah.
some certain bits, like maybe bit 30th or so, 30th, 29th, they both actually are set. We can make a big range out of that also. So we cannot generalize so easily on this problem, right? So by just looking at the input and output. But one thing is very sure in this case, like if if I have like the 30th bit set, right, and
Okay.
also that bit is set in my both of these input and output, input one, right, and the input two. if my 38 bit is set, right, then I can easily say, okay, I say, okay, that bit actually will come into my answer, right? So it depends on the other bits also, but I'll have to look for the other bits. It depends on the distance between both of them.
Mm.
Numbers, yeah.
So you saying going to the from left to right,
Yeah, I
or
was thinking
right?
that way.
Yeah,
Yeah,
yeah, yeah. Yeah. That look good, huh?
right. But
Because
in this, but one observation again, if my 31st bit is set, right, and my 30th bit is set, but then I cannot make that observation because I think I have to see both of the bits are to be set. That's very important, right?
well, let's think about like make it small, right? Like make it
Uh-huh.
instead of make it 30, we make only 4 bit only, right? So that
Okay.
uh
So what do you
so
want
we
me
have,
to do?
yeah, 0 0 0 1, right? First
Uh-huh.
we have, oh yeah, let me see. Yeah, we need to find the lower bound. Yeah, I see. Yeah. Because I'm thinking same as your, right? Because if the 31 bit is set,
Mm-hmm.
right,
Mm-hmm.
then that means the rest of the bit, there's somewhere in between the range, the rest of it will be zero if we start from zero, right?
Mm-hmm.
Because to get to one right there, we have to go through all zero ones, and two, three, and all that bit at one point, one of the bit already set to zero,
Right.
right?
Mm-hmm.
So if that bit is set, the rest will be zero. If we
Mm-hmm.
start from zero, but we start from somewhere else. So how we take into, how would that help?
Mm-hmm. So also the bits on the lower side, they quickly become zero because the first bit actually is alternate between 1 and 0, right? Correct. So the second bit actually alternates like it is at 2. When it is at 2, it is set, right? Then it is not set at, it is set at 3 also, but it is not set at 4, right? And it is not set at 5 also. Then it is set at
Mm.
6, right? So it is alternating between 2, right? So, but the first bit is always alternating between 1 0 1 0.
One distance, yeah.
Mm.
Yeah, one distance, correct, something like that. Yeah. So if you see the third bit, it is almost similar, I think, right? It will be 3 will be 3, right? Then
Three
for,
distance.
oh, so it will be for 4, it will be for 5 also, it will be for 6 also, and also 7, right? For 8, it is not going to be. So in this case, it will be like 4 bits will be set to 1.
Mm.
Okay. So then for 4 bits, I think we'll have 0. Similarly, for the fourth bit, actually it will be set on the from 0 to 7. 7 times it will be having zeros, right? So these will be 7 zeros or 8 zeros, and then on 8 you'll have 1, right? Then 8 you will have 1, then 9, 10, 11, 12. So you will have another 8 bits, 8 positions, it will be 1. So that is the way it is incrementing always. Okay. It's always alternating one after another, but here it is by 2 based on where the bit distance is, right? So because it is based on the power of 2, correct? So here it will be 2 raised to 3, which will be, oh, 2 raised to 2 in this case, right?
Mm.
Yeah. So and here it will be 2 raised to 3, right? And if it is 5, it will be the same thing, right? 2 raised to 4 and all that stuff. So if you look at, if the distance between both of them are something like this, okay, so then you are sure that you will be having a 0 always for this particular bit. Okay. So that was thinking, but then if now it is more clear also, right? So we have to see, we have to just look at, instead of going and doing each and every adding of each and every element, we can just look at these two inputs, correct, and look at the very extreme rightmost bits, start from there, and if they both are set, okay, so then we can count them, and then correspondingly look for the next rightmost bit, right?
Yeah.
Rightmost or left?
Leftmost, sorry, leftmost bit, yeah. So just so to go to the leftmost, then we'll have to keep on removing the rightmost bit one by one, correct? So till we don't get both of the all both the numbers having almost, yeah, it will have the same values because we are removing all the rightmost bits one by one, okay, and just compare the two numbers, input and out, input one and input two. If they are not same, we again do the same thing over and over again till we don't get the numbers to be same, and then we can just return one of the number, right?
Mm.
Something
Can
like
we
that.
yeah,
Mhm.
can we do an example for 5 and 7 and see how it works? So 5 will be 101, right? And 7 will be 111.
Triple one.
Right. Okay. So sorry for the first bit. I'll just make that as 0. Okay. So this is 0, right? Okay. So in this case, yeah. So this bit and this bit, they are the ones on the very left side, and they are common. So they will. This bit will stay. Correct.
Mm, okay, because let me see. Okay, but like the one you draw before it, like all the bit is on, one is on, but at one point it could change to from 1 to 0, right? Could it change from
Yeah.
1 to 0, but
This won't change. This bit will never change because the range is like that, right? So whenever we have a range in which the input 1 and input 2 has a bit set at the extreme left side, okay, so that won't change because we have set up a range now.
okay.
So we are not going to exceed this range, right? So our numbers are going to lie between that, and therefore the extreme left bit will never change. But had it I had a left bit over here and one left bit over here, then it would be not the case, right? So
But
because they are not on the same bit positions, then it will be 0.
I thought last time you draw it, the change, right? It was like uh, 1, 1, and then 0, 0, and then 1, 1 again.
6. Let's say 6 comes in between 5 and 6.
Yeah.
So at that position, yeah.
So the bit pattern, let's see, we're at the second bit, there was like 1, 1, and it changed to 0, 0, and then 1, 1 again.
Yeah, but in this case, how many numbers you are going to have? You will have only 0, 1, 1, 0, correct? And that's all. You're not going to have anything more, right? Because the
Because 7
seventh
is the
number is
last.
that. So the distance from these two will always be the same. So if you say that if we have to have a 0 in between this range,
Yeah, I would
okay,
think in that case.
so for that case, your this bit will have to be set along with this bit. So you cannot have this bit set at the same position. So that will never happen,
Mm,
right? So okay, the way I was saying it for this one bit, right? So we always have 1010, correct? So but
yeah.
if you go for the second bit, you know that for it is set for, I think it is 2, right? Then 3 also it is set, and 4 it is not set, and then it is set at 5. It is not set at 5 also, right? So it will be set on only in 6, and then it will be set at 7. It won't be set at 8. So it is like two distance apart. But when you come for the third bit, so it is set at 4, it is set at 5, okay, and then it is set at 6, and it is set at also 7. But it won't be set at 8, 9, okay, 10, and I think at 11 also. Then it will be set at 12, right? So it is four distance apart. So if your number is between these two bits, right? Okay, so you are sure that it is always going to be 1. But you cannot have this one and this one over here
Okay.
because your this bit will be set in that case, correct?
Yeah.
Therefore you are coming here. So whenever you actually move from this 1 to another 0, okay, and then you come back on another one like this, so you are sure that another bit is already set, right?
Right. Yeah. Yeah.
So
Yeah.
that is very
That's
important.
very
Yeah.
So
important.
you have to be in this range. So it becomes more easy to visualize when actually you go to the higher bits, like when you go to 31, 32, sorry, 31 and 29, 27, then you have these ranges are very big, right? So they are huge ranges.
Mm.
So you can stay on the same bit for a very long time. But here we are on the very small distances, therefore it doesn't, you can't visualize very well, right?
Mm. Okay. Great.
So that is very important, and I think so. If we keep on looking for the numbers at the right side, if we take the very simple example like this 0101 and 0111, right? So we know that these are the two right bits, sorry, left bit, which we want to keep. Okay, so just start with this position always and try to, because this number is not the same, right? So if we say this is A and this is B, okay, and we try to compare these number is not same, then we try to remove these two bits. So when we try to remove these two bits, so we have that formula, right? The famous formula. We can remove that adding of A minus 1, right? So we can actually easily remove the last right bit, right set bit. If I use this formula, so I can remove this one bit. So do the same thing for both of these numbers. Okay, so and then just compare if the A and B are same. If it is not, again keep doing in a while loop. So because you'll have to remove these two bits, two set bits. So this is nothing, this is not set. But if you remove this one, okay, when you make it to 0, and then you compare the these two numbers now at that time, it will be the same, and then you can return the number. That is one way, and I think Shashank did it a different way. So that also makes sense, right?
Yeah.
But in
It's the
that case,
same, like implementation is a little bit different.
right, right. But you actually go all the way left shifting, right shifting, sorry, and then
Right shift.
again you left shift it, right?
Yeah.
Yeah. So you can either do it that way, or you can actually keep on removing the set bits one by one.
Yeah.
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 Yeah, this is a very easy problem, right? Even if they say medium.
Yeah.
Mhm.
No, but we have to visualize that pattern. That's it.
Yeah, yeah. And we have been doing such problems for a long time, so it's
Yeah.
easy to come up with. Yeah. Yeah.
So
So
in your position, you go from left, right, from right towards left.
from right towards left, yes.
So
So you
what
can,
you do after that? I mean, this.
okay. So if I have like this as M, okay. So if I have M, the way they are saying, right, we'll take M as 5, okay,
Yeah.
and N as 7, okay. So what I'm going to do is I'm going to compare M and M always. So until and unless that the way you are doing in the while loop, right?
Yeah.
So if they are not equal, okay, then I'm going to make them equal. So how I'm going to make them equal is I'm going to remove one right bit for both of them, right? One right set bit, one at a time.
Okay. Yeah.
Well, actually, I won't do that. I think I will only do with one left bit, sorry, one right bit of the biggest one, that is the n, okay, and I'll do it in such a way till this doesn't become lesser than this value. So
I'll try
when
to
that
do.
is lesser, so I'm sure that that will be my uh, the what you say the most common bits between both of the numbers,
Yeah.
right? So if I just keep on doing it, but either way I can do it that way also the way you are doing. Okay, just keep on comparing. So I can remove one left bit at each and every time. Okay, but in that case of M, I'll have to see if my that sorry, that right bit is set or not, right?
Yeah.
Or if I
Yeah.
remove the right bit way ahead, then it'll be a problem. Yeah,
Exactly.
yeah. So that is that thing I have to keep in mind, right?
Yeah. So here, like I'm going from left to right. I mean, doing the right shift and just increasing my I. And whenever you find your M is equal to N, you just, I mean, I will store all that iterations, right? And you those many left shift at once we are doing on this bigger number and returning.
Yeah. So
Yeah.
I think this makes more sense, and it's easy to even follow, right?
Cool. Yeah.
Yeah.
Do you want to share?
Okay, I can share that one. Let me check. Yeah, so this is the way I was saying, but yeah, it's not so easy to come up with because yeah, you handle these base cases and then you keep on comparing. So you keep perform that operation on only on the upper bound, which is n in this case. You keep on removing the leftmost bit, right? So
Yeah.
when you remove the leftmost bit, always you will have to compare that with the lower bound. So in the case when your lower bound is smaller or equal to your upper bound, okay, then you can stop and then you return n.
Yeah.
But
Is it
you won't be able to visualize immediately there, right?
you
Yeah.
keep return? I mean, you keep remove the rightmost bit, right? That not the left.
Yeah, sorry.
Right most.
Yeah, you're right. Yeah.
Yeah.
Thank you.
And
Yeah.
then it, okay, until when it's 0, right? And then
Yeah. So I just keep removing it unless and until this condition is satisfied. I keep removing it. If it is not satisfied, then it breaks the loop and then it will return whatever that n value is. Yeah.
Makes sense.
I
Yeah.
see. So let's say m equals 7 and n also equals 7,
Mm-hmm.
right? Then we going through. Oh, it's not. Yeah, not less than the while loop condition is not met, so just return
It's
7.
7.
Right.
Line number 14 will be executed.
Right.
But
It
does it
won't.
return 7 or return 3? Oh yeah, return
It has
7.
to return
And
7. Yeah. It
7
won't.
and 7 is 7 only. Yeah.
yeah,
Yeah.
3 bit, but it's 7, value 7.
Exactly.
Yeah.
Sure. Sure.
Mm. Yeah.
Yeah. But yeah, sometimes you actually tend to forget this. Whether I will be able to satisfy this condition because I started with okay removing the rightmost bit for both of them, but actually to visualize it looks fine
Mm.
because you are sure that what is your rightmost bit, which is a set bit, right? But there can be bits which are set in the other range of the bits, like the 7 and 5. They are not on the same the bit positions, right? So that might be a problem. So this is the only condition you can compare. Then that might be a slightly different way of doing it, yeah. But I think what Shashank did is more easier to come up, right?
Yeah.
Yeah.
Yeah. We can move to next one.
Okay. Yeah.
So next is our like linked list components. So we are given the head and the head node of a linked list containing the unique integer. Now we are also given the list G and a subset of values in the linked list. We have to return the number of connected components in G where two values are connected if they appear consecutively in the list. Like 0 and 1 is appearing consecutive, right? Even 3 and 4 are connected. So 0, 1 and 3, 4 are answers. Other two connected components in that case, yeah. Oh,
Two connected component. Let me see. So we could have picked 1 and 2, right?
but that is not in your G, right? I mean, it should be in Z also because what they have said, we are also given a subset of values in the list, right? You have to return the number of components in the G where two values are connected if they appear. First, you have to check in the Z, and depending on that, you have to check whether they are connected in the list or not. Like this example, like 0 and 3, you look, they are connected. No, they are not connected, right? 0 and 3. But if you see 3 and 4 are connected, right? And 0 and 1 are connected. Based on that, you'll have to give, right?
Oh, only two consecutive one, and
Exactly.
it have to be. And G, okay, in this case, G is in any order. Huh? It doesn't.
Yeah, because it's a set. G is a set, right? So order need not matter. A subset of values in the list.
What
No,
does it
they are
mean? It's a set.
not set, subset. Okay, okay, it's a list of values only.
Mm.
No. But order doesn't matter, I think, isn't
So
it?
that is what it's saying. But then in that case, okay, so because what comes to my mind is like it's a linked list, right? So you are always going through in the linked list, I'm traversing the linked list sequentially, correct? And if the linked list is always ordered, then I would think my G also should be ordered, right?
No, but that's a subset, right?
Right, right, yeah. So
Okay.
I'm just thinking that way,
Mm.
the way
Uh,
Leon was on, right?
Can I
Yeah.
ask a question here? Regarding the first example, if we add 2 to G, what should be our answer? If we add
One.
2, value 2 to
One.
our set, just one?
Yeah, because entire is connected by one. So I mean 0, 1, 2, 3. You are telling that if you are adding 2 to the Z, right?
Yeah, yeah.
Yeah, then it will be 1 because 0, 1, 2, 3 all are connected.
Okay, thank you.
Yeah.
Yeah. So if we add 2 to that, so it means it is asking us that G is also part of that, okay, subset, right? The list. And
Yeah.
then if we keep looking for each and every element in the list, it is a part of G. So that becomes a single component. Okay.
Exactly.
Okay. So I was thinking, like either you cannot do anything on the linked list. You cannot make it ordered if it is not ordered. But you can at least make G ordered, right?
Okay.
So just
Okay.
sort it. But that also won't help because here it is showing the linked list as a ordered one, but it might not be ordered also, right? They have
Yeah.
not mentioned it anywhere, so we can't assume it also.
No, they haven't mentioned anything.
Yeah. So then in that case, if we sort the G also, that won't make sense.
Yeah, there is no point. Yeah, exactly.
There's no point in doing that. So then we can actually do it slightly different. Okay. Then we'll have to go and search for our component, the input value of our linked list every time in the G. Okay.
Yeah, and whether the next is available or not. If it is connected, then it's one component.
The next one is available or not. Okay.
Yeah.
Uh-huh.
Like is I mean 0 is there. Zero's next is 1. So we'll check whether 1 is in our G or not. It is. So it is one component. And again we'll check whether 1's next is 2, but 2 is not in your component, right? I mean sorry, in G. So you got 0, comma 1 as one of them.
Mm-hmm.
Then you will start from 2. 2 is not there, so there is no point in proceeding further. No, there is point, right? Till the point you hit the list. 3 is there, but three is not connected to any of its next because at this point we made sure that 2 is not present. So there is no point in, we won't be going back, right? It's a single linked list.
Right.
Yeah, so had it been a double, then that will be more. What do you say?
Yeah. But see,
Yeah.
the only the observation what here is like if we come to 2 and the 2 is not a part of G, okay, then we ignore 2 completely. We don't even take into part of our connected components. Okay. But if you come to 3, 3 is a part of G, but even though it's a single element, we take that as a part of connected component. Correct.
Yeah,
So whatever numbers are absent in the G, they are just ignored.
yeah, and then just look for the ones. Okay.
Mhm.
But
Makes sense.
3 is not two consecutive connected, right?
It's not
Why
connected, but
why
it's a
is
part
not?
of G, so you have to take it.
Yeah. I mean, node in itself is a connected component if it's
Yeah, but
isolated.
then in that case, it's not the case for 2 because it is not a part of G.
Not a part of G. Yeah.
Yeah.
So you have to make sure before checking in the list, like whether that is present in Z or not,
Hmm.
depending on that you decide. Okay. Yeah. So it's like more trivial only, right? I mean, I don't think so
Yeah.
much we can do
I
here.
also think that the question
Go ahead.
description is kind of a little confusing.
In
Yeah.
what sense? Yeah. Like,
Yeah, because the G also, right? If you look at the G, the
hmm,
first example, now we are discussing, it doesn't include the 2, but includes the 3, right? And they have not
yeah,
very clearly specified in the problem statement. That makes sense.
exactly. Yeah.
Yep.
So, yeah, we can. You want to go? You want to share shuffle
I did
something?
it's the same code as yours, just in Java. Yeah.
Oh, so this is like, I mean, just creating a set so that to avoid any kind of duplicate. So they haven't mentioned that there will be any duplicates in Z, right?
Right.
Okay. So
So,
this is
yeah, that is an assumption what you did. And exactly, I also did the same assumption.
yeah.
I thought, let
Otherwise,
me try with this. If it works, it's good. If it doesn't work, then I'll go back.
we'll have to change. But
Right.
that will be a clarifying one, right? Because there could be two connected to two in the list, right?
But that's fine, right? Even if it's duplicate, and if we just take single number, so that number is always there. Doesn't matter, right?
Mm,
So if it's a duplicate, so
mm,
the G will always have either, in this case, if we had something like a 4 which was duplicate, and if we had a single 4 in G or a 2 4 in G, it's not going to make any difference, correct?
difference in that case, yeah, because they are connected only. Yeah.
Yeah.
So it's just asking how many connected components, just the count. That was always asking. And yeah, I wish they would have rephrased the question better, but that's okay. Yeah.
Yeah.
Yeah, but that's what we'll have to ask clarifying questions.
Yeah.
That's important, right?
Exactly. Yeah.
Makes sense.
But I really like the logic over there in that if statement. We did it with one, basically one pointer. Initially, I was going with two pointer, but with that logic and line number 11, you could do it with one pointer. That was really cool. Yeah.
Yeah,
Yeah.
I never did that way. I did the very basic way, but yeah, this is a very out of box thinking also, right? A trick to handle this case, yeah.
Yeah.
Exactly. Yeah.
Especially the last one, the
Yeah.
last
Yeah.
three, yeah.
Yeah. For the last one only, we are doing that head dot next dot well, right?
Hmm.
Yeah. Otherwise, so yeah, just we are checking the value at the head is present in set or not, and next node should not be none,
Hmm.
and its val should not be in the set G. Then we consider it as one, because if the value is present in the Z, then it will not be a connected component.
Yeah.
Yeah. So and then just go for the next head next.
Yep.
Yeah. You want to share shuffle? Like,
Yeah. I can. This is my code. I can just share it quickly. Yep.
let's see in Java how it works.
Yeah. Oops. So in Java, let's see. Let me pull up that question. Uh,
It's 817.
so I'm doing exact same thing, right? Um, Intuition is okay as soon as it says, okay, the linked list contains a unique integer values, and G is an array, and it also has a subset of the node values from the linked list. I immediately notice, well, we have to put this in a set. Why? Because the source operation and has set is O of 1. So that's what we did, right? We put them in the set right away. So when we do have to look as we traverse to the linked list, we can easily search it. Now, so okay, now we're just traversing the list. And the intuition behind this is um, the question is basically asking how many number of connected component linked list, right? So if you look, 0, 1 is one component, right? And 3 is another component. Now, it doesn't have to be next to each other. Now, if you, in example 2, it says 0, 1 is one component because 0 and 1 exist. Uh, 3 and 4 is another component because 3 and 4 exist. That's why the output is 2. So what we do is we loop through the linked list, and then line 27 does the handle most of this operation. So what line 27 does is, okay, we have all the node values in our set. Let's just look on our set, if it contains the node value, and that's what it does. It looks, but look in a way that, let's say, let's walk through this example. uh, 0, 1, 2, and 3. So my node, let's say I'm looking at node 0 right now. My current is looking at node 0 right now. It says, okay, my set has 0. Good, because it has 0. Now it's checking, and is my current node is in the last of the linked list? No. Or my next value, if it's in the linked list, it is, right? So we want to check if it's not in the linked list. The reason we check if it's not in the linked list is if the next node value is in the set, is if the next value is not in the set, in the hash set on my case, then the current node must be at the end of the component, linked list component, right? Let's just say if we, so on the first loop, it finds 1, so it's in the set. So then it traverses one more time. And the second loop, it's at 1, right? And then it checks, okay, if my set contains current.val, current.1, yes, it does. Then it checks, does my set contains 2? It doesn't. That means, okay, if my set contains, it doesn't contain 2, then we are at the end of the current, connected list. So that's why it increments the count plus plus, right? And then it loops again. 2, now this doesn't work because 2 doesn't even contain in the on the set. It goes there. 3, now 3 contains. Now it checks, is 3 the last node? Yes, it is. And then it count count plus plus, and that's how it outputs 2, right? Same way, same logic here. And I believe the time complexity is, now if you look, we are looping all the nodes in the list, so it'll be n plus, since we added the n the g dot length, because we had to traverse to this array to put them in our set, so it'll be g dot length, so n plus g dot length, right? Now space complexity would just be g dot length, because we only used whatever number we had in our hash set. And yeah, that was the end of the problem, but interesting problem. Yeah.
Yep, that's good. Yeah.
Any
Yeah.
way we could have tweaked this problem a little bit more?
So in fact, this is the most efficient way you guys both have implemented, right? So I can't think anything more efficient than this, right? So
Yeah.
because the way I started was much less efficient, in the sense I'm not handling the case the way you are handling it here for the last element, right? Because you won't be able to check the last element if you are just going in this while loop, if you don't use that condition what you are using current dot next val.
Yeah.
Yeah, so that's very important because that never comes to me so quickly. So usually I end up checking that condition outside the while loop, but you are doing inside the while loop. That's the most important thing. Yeah. And also
Yeah.
I was using two variables, like you are using the count variable here, which you are going to return, and I was using another variable to keep account of how much connected components are for a particular component, how much connected elements are for a particular component.
Mm.
So in fact I was using two variables, so you are using a single variable and also checking the condition in the while loop. That makes more efficient, right? Yeah.
Yeah.
That's good. Yeah.
I'm gonna stop the share then.
Yeah, then we can move to next.
Yeah.
Okay, sure. So our next problem is like a binary watch. Yeah, nowadays. So it's a binary watch has four LEDs. The top represents 0 to 11 hours and six LEDs on the bottom. 0 to 59. Okay. This is 0 to okay. And each LED represents a 0 or 1 with at least one significant bit on the right. They have a binary 325. I mean, the current timing, this is right on the watch.
Mm-hmm. 3 and 25. Yeah. 16 and 20.
25. Yeah.
So we have 10 LEDs, right? 4 on the top and 6 on the bottom.
Bottom. Yeah.
Hmm. Well, the very first thing, if I just look at the problem, if you just scroll up, you know, uh, and it says easy. I don't
Yeah.
think so. It's an easy problem.
Yeah. It's not exactly. Yeah.
At least implementation wise, it is more than easy. I won't say it is almost hard for sure. It's not hard.
At least
It's
medium it should
closer
deserve.
to medium. Yeah, it might not be medium, but it might be closer to more than easy. It's more closer to medium. Hmm.
Yeah.
That is what it is. When I looked at easy, I thought it might be a very quick fix, but it took a long time to actually do this, right?
This year.
Even to
Probably that's why
understand
it
what.
has so many downvotes, right? Maybe people.
Okay, yeah.
Oh,
So if we make it medium, then the downloads will go up.
Yeah.
Okay, that's true. So then, how do we approach this problem?
this one. Yeah. The order of output one. Okay. It represents and then currently written all the possible timings that watch could. So you can do this thing, right? Four are on the top, right?
Mhm.
And six are on the bottom. So
Right.
what you can do, 4C1. I mean, you'll have to take possibilities like this. What do you say?
Correct.
From first 4C1 into 6C1, this could be one possibility. Then 4C2 into 6C2, and then 4C3 into 6C3. This is one. Again, from top you can take one, from bottom you can take two. Like all the possible, what you say, if this is M and this is N, M cross N possibilities will be. Those are the possible timings that we can generate out of this watch.
Mm-hmm. Well, that is good. So, a very high level, yeah, this is
Yeah.
the complete combination what you're talking about. That's perfect. Very ideal
Complete.
solution, I would say. But with the way I was thinking, so
Yeah.
we would start with, say, like bit one only one LED set. Okay.
Okay.
Oh, then I will start with two LED set, three LED set, four, five, six, seven, eight, nine, 10, and then I will form something like a map. Okay, so I will
Yeah.
say like if I have one LED set, then I'll do actually basically a lookup table. If I'm setting one, so I'll place that one at every position. Okay, and that put that in that map as a list, right? So I'll do the same thing for two. I'll do the same thing for three. Okay, I won't actually worry about whether it makes a valid or logical sense, right? I just keep on putting all the values,
So
right?
in map, what will you do? Come again?
So I was trying to say like it will be a lookup table, right?
Okay.
So, so very high view will be like if I have only single LED set, right?
Mm.
So this is for one LED set. I will have a list. Okay. So for the two LED, I will have another list. So three LED, I'll have something like four. So so on and so forth. I'll go till 10, right? Because 10 is the maximum. So every time I put 1 year, okay.
Mm.
So this whole thing will be actually something like I can say it is a string of maybe 10 okay, 10 characters, something like that, okay. And
Okay.
then if I put the string here, something like 1, then 0 0 0 0 something, so other will be 0, some big string like that, you know. So that actually will be 1. Then this one actually will move from the last extreme left to the second left, like that, you know. So I will keep on having a string like this. So same thing I'll do for 2. Okay, but in this case I'll have these two set at two places, but it will have a huge number of strings, correct?
Yeah. In
And
that case, yeah.
I'm not really worrying about if they are the valid numbers, because if in this first four LEDs, if I have all of them set to 1, in that case it's going to be 15, and it's going to be more than my input, sorry, more than my valid output, right, which is 11. But I won't worry about that for now, so I'll just keep on populating this table. Okay, so whenever I come to any of these numbers, say my n is equal to 3, so I'll just deal with this particular elements which are in the table.
So 3 means 3-bit will be set, right?
3 LEDs will be set. Yeah,
LED, any three out of those many LEDs, right?
yeah. So, but it'll be like a combination or a
Yeah,
permutation, I would
that is
say.
what I was saying. Yeah.
Right. But it will be a brute force, right? So I'm just
10C3
thinking,
kind of.
yeah. So
Yeah.
on a very high level, and I have the luxury of the space as well as the time, right? So I can do it anyway. So I'm doing it to just
Yeah.
get an understanding of it, the problem, right? Because as I said, the problem is not easy. It took a while to actually understand,
Yeah,
right?
that's yeah.
So I was thinking, okay, this is one way, the brute force. I do all the permutations, I keep on adding that in the lookup table. But even if you look at it, you know, I really don't need to add everything in the lookup table, because my input itself is this, right? Okay, it is always going to be one key, so I don't have to completely create the whole lookup table, right? I can just create this list also, that should be fine.
Yeah,
Okay.
and there won't be any duplicates. I mean, like corresponding to 3, you set any 3 bits, right?
Hmm.
And in 2, by setting 2-bit only, you are getting the same number. It's not possible, right?
So you'll have to generate the permutations that way, so they won't have
Okay.
any duplicates, right?
Okay. Yeah.
Yeah, yeah. So then that comes, you know. So if I have a key value, I can easily, if I can create the whole table, okay,
Yeah.
so I can surely create this list of for 3 or for 4 on the fly, right? All the permutations.
Yeah.
So if I can do that, then I can use our famous algorithms of backtracking, which we use for permutations, right?
Exactly. Yeah.
Yeah, and then I can do it slightly better. Uh, then that might actually converge to a solution, even though it's not a very great solution, but at least I have a solution.
So you had to hard code all those strings then, right?
Right, right.
Okay.
Yeah, that's not a very good way of doing it, but at least I have some problem, you
Yeah.
know, which to work with.
Yeah. No, at least you were able to understood it. I looked at the problem. I'm just like, nope.
It's like
I'm gonna go to the medium problem.
Yeah, yeah, it is difficult problem. Yeah,
Yeah.
I also had to take the help of a lot of stuff. It's not so easy to understand, absolutely. Because
That's what I was
the way
thinking.
they are putting it. Mhm. Yeah, go ahead.
I look at this problem as I think somebody touched in the beginning. All possible, let's say you have here 10 buttons, right? So if you have k of them are on, so generating all possible k subsets from n elements, right?
Right.
And then I think then we can use the recursion approach, right? And for
Yes.
every time you go down the tree, you just say I pick this element or do not pick this button, and create a time for that. And you can keep the time in a map, and if you have a duplicate, you just you know and
ignore it, kind of. Yeah.
Yeah.
Sounds good. Mhm.
Yeah, that can actually make it workable. Yeah, so you will have to validate the timings, right, every time. And the good thing is about you can return the value in any order.
Right,
Hmm.
right.
Yeah, so that should really be fine, and I
So
think it might be
he's,
acceptable.
I think you are also generating all the possibilities only, right? Kind of brute force only, isn't it?
Yeah, I
Root.
was wondering, without doing that, uh, how do I know that, I'm not generating all the possibilities?
Yeah, that's
Hmm.
the point.
Yeah.
I mean, in some way, you have to go through create the entire list first, and then say, okay,
Hmm. Yeah. Then
So for creating the list, you always take the help of recursion, correct?
yeah,
And
yeah.
you just create that, and then the way we do for permutations, because at least the permutation pattern is slightly we are able to follow now. I'm not saying it's very well conversant with us, but at least we are able to follow to some extent. So some way we will be able to create it using a backtracking and a recursion, right? Yeah.
Yeah.
And then the thing becomes only of validating the timings. So for that you can use a lookup table also. Yeah, an extra lookup table. Yeah, makes sense.
Yeah. Sure.
Rudra, do you have any implementation you want to share? That similar one?
pardon me.
Do you have anything to share?
Oh, no, no, I I didn't code it up. I did a similar problem where basically, if you have a given set of elements, right, you generate. The problem was to create all possible, k subsets of that set.
Oh,
So I was
okay.
trying to, cast it in that form.
Okay.
Right. Yeah, that's fine. Yeah, no problem.
Yeah, maybe next time I should be prepared with the.
No, that's okay. I was just thinking if you have something to share,
No, no,
that's
I did
fine
not
as
write
well.
it
Yeah.
up.
No
Sorry.
issues. Yeah, that's good. So okay, so I have something on the similar lines, not exactly that. Let me share that. Okay, just
Sure.
share. Okay, what I was doing here, right? Okay. It won't be exactly the same, but slightly on the similar lines. Okay, let me go there. No, it's not the one. Binary version. Yeah. So it's slightly different, not exactly the same. Uh, so this was the way I was doing. Uh, these are some of the base cases what I'm trying to handle earlier, and this is my string. Okay, so this is the string of all 10 zeros, which represent the LEDs, and then this is my recursion function, helper function. Okay, I'm passing the string. Okay, and then passing my current index. Okay, you can see that, and then this is the num what I'm getting from the input, and this will be my answer what I'll be returning. So this is that recursion function. So when you come here, so these are the validation conditions of our all of the string. Actually, I form a substring for the top four LEDs, and this is the first, the hours one, and for the minutes I'm actually forming the next six ones. Okay, I'm just extracting from my input WST TSTR. Okay, so if they are not valid, okay, I just return them from there itself, or else if it is not, so if this is the bits, right? Okay, so this bits is what is the numbers what I'm getting from here, the num. Okay, so this bits is equal to 0. It means that I'm at the end of my recursion. There's a base case. So I just formulate the answer based on whatever my hour and minutes are. Okay, and then I push it in my answer, which will be a vector of string, and then I return. And this is the permutation part, right? So, so what I do is actually I start with my position and I go all the way to the end of my string. and every time I actually add 1, okay, to the position of this particular string, and then I do a recursion. And then when I do a recursion, I just increment my this position to 1, okay, and also I decrease the number of bits because I have already added 1, so I'll have to decrease this number of bits, right? And when I come back from the recursion, if things are not satisfied or they are completed, right, so then in that case I have to again remove this one, right, because it's backtracking. So once I'm setting it, then I have to undo what I did earlier. Okay, so I can get a permutation. So if you look at it, it's very easy to follow the permutation part, right? If we actually uh, follow this permutation pattern, right?
Okay.
Yeah.
Yeah. So that's the only small trick in this, and here you actually
It's
extract. Hmm.
it's include backtracking exclude that template,
Right.
right?
Yeah.
I mean, we discussed other day, like we have 11 questions, which basically include backtracking and exclude, and this is also one of them, I
Mm.
think.
Hmm. Yeah.
Yeah, exactly.
Okay. Yeah. So that would be a good thing to put on that list. Okay. Cool. Yeah. Yeah. So
Yeah.
if we now the problem looks very straightforward, right? Because I was
Yeah.
also not able to visualize the way when it was said in the WTSTR, actually put all of them in one string. Okay, don't bother of it. Then I was trying to understand how I will handle that. But if I extract any of the way, like the first four as four LEDs and the six as the next six LEDs, because I'm free to do any way I want, right? Yeah, it's only the
Yeah.
composition and then just putting this in the backtracking, then we have a solution.
Understood, yeah.
Yeah. Yep.
Yeah. Sure.
So, but that might not be the best way to do it, but we have a solution, right?
Yeah. At
Yeah.
least you have.
Right. Yeah.
I think, I don't know. It's long back I took it from solution.
Okay.
What? Let's go. Let's see. So this is like if your num is 0, you return this time, right? And now I'm setting my bit like for every I 10, 10 like 2D array I'm creating, right? For
Mhm.
every I 10 that 1, 2, 3, 4 list of it will have.
Mhm.
And now what I'm doing, 10 minus num plus 1 to 10. So num is like, let's say for this current you want to, I mean, they gave you the current time, right? An integer n will be given currently. So we are subtracting that from the num and going to the 10. But why? Okay, I mean, whatever timing will be, it will be from that number, 10 minus number to the last 10 only, right?
Yeah. So here the thing is, what happens when you have a number. That
Okay.
number, if it is greater than 3, okay, there are two things going to happen, right? So one, because your first four LEDs cannot display time more than 3 number, right? Because if you give a 4, it is going to be 15.
Yeah, 15. Okay.
So that is not possible. But in 3 also, they cannot display 12. They can only
Eight,
display 11,
11. Okay. Yeah. 8 to
right?
1.
Yeah. So therefore, actually, there will be a differentiation if the number is greater than 3. Okay. So then you have a chance to split them across the hours and the minutes.
Yeah.
Okay. So, or if it is less than num, so you can easily consume all of them in the hour or all of them in the minute. Right.
Oh, okay. Yeah. Makes sense.
And or else you can have a combination of an hour minute also.
Minute both together.
Yeah.
Yeah.
But if it is greater than 3, then you cannot actually avoid hours and minutes. You will have to take both of them together. Right.
If it, yeah. Okay.
So that is what has to happen. If see if it's a number 4, so you will have to still take okay, if you take all the 4 in the bottom, okay, so that might be fine, right? if we take all the 4 in the bottom.
All the 4 32 16 that you're telling.
Yeah, in the minutes one. So that should be fine. Okay, yeah.
Yeah. Okay, yeah. Because it won't lead to even cross R. Okay, yeah. So if all are on in minutes, how much will it give? 32 16.
No, that will be more than 64, correct. So it is 30, it will be 63, correct. So if we
So
take all of them on,
one
so in
hour,
that case, yeah,
more than an
okay.
hour.
So in that case, you will have to split again between both of them. Okay, but you cannot take or. Okay. Oh yeah. So if it is less than or equal to 3, you can have them in the minutes as well as hours separately or
Okay.
together also, right?
Yeah.
But if it is greater than 3, you can have them in the minutes, complete all of them in the minutes, or you can have a combination of hours and minutes, but you cannot have just a combination of hours, right?
Yeah.
Yeah. So that's the only small distinction. Yeah, but yeah, so the way you are going is also, yeah, the right way to do.
Yeah. So that is what I'm checking. The time in my bit set, right?
Hmm.
And for what you are doing, for every bit, whatever time I have got, I'm taking the last one of it and adding one to that.
Hmm.
From that range to the max bit plus one. This part I like I'm myself is not sure. Is for every bit in the range of to the new bits we are adding the time and the current bit value.
Okay.
I'll have to cross check this, I think.
Well, yeah, that is fine. So
Hmm.
maybe like if we have something, the input, whatever your input is num, right?
Okay.
So you can actually divide that. Okay. So now if you consider that you have a sort of a hours array, and you have an hour for and another array for minutes, right? So if
Okay.
your number is of certain value, okay, then you can split between hours and minutes. Okay. So what you can do is, if number is 3, okay, initially you start hour with 1, okay, and whatever is remaining you put into the minutes. Okay.
Okay.
So for 1, you actually look for, if it is 1, what will your valid hours will be. Okay, if it is the 1 is valid 1, you can add that to the array. Okay. Add that to the result, but before you add to that, you will have to go and check for the minutes also. So whatever the minute combinations will be for 2, right?
Okay.
So
Yeah.
for the 2, you keep on iterating for all the minute size. Like your minute size are very constant, they are from 0 to 59 only, right? So whenever you go to 0, you see if it takes 2 bits. If it doesn't, you just ignore it. If you go to 2, it takes 2 bits. No, when you go to 3, you know that it takes 2 bits, right? So you add that to your answer list, and then you add your number 1, whatever your r was, okay, with the 2 of your minutes. Okay, so it's like a sort of a graph solution, right? You are taking the node of an hour, which is 1, and then you are trying to go its neighbors, which are the minutes. Okay, but you are just validating if they are fitting in that particular bits, and then you are forming an answer, and then you are adding that to your list of our answers, right?
Totally.
So yeah, so when you do with 1, you go for our move to 2. Okay. But the same story you repeat for minutes. So when you are done with that particular 1 bit, then you increase your hour from 1 bit to 2 bit. Okay. And then
Okay.
whatever is remaining, it's because our earlier number was 3, so your our minutes are remaining with only 1 bit, right? So again
Yeah.
you do for the same in the way you will do for the hours also, because for hours also you will start from 0 to 11, and you will see if how much of them have 2 bits. Right now we are looking for 2 bits. So you come to see the hour which has 3 bit, 3, it corresponds to 2 bits, right? So you will take that hour and then you will actually iterate on the minutes part again. So in this case, the minutes will be of only 1 bit, right? Then again, you'll start from 0 to 59 and check if it is again using 1 bit. If it is using 1 bit, then that will be a part of our answer.
Yeah. So line number 13 is running for minutes, right?
Line is the 13 is running for minutes. Yeah, right.
Yeah.
Because
Makes sense.
the other one is for
Hour.
plus 10. Yeah, it is
Yeah.
10, right? 10.
Max bit is for hour. So max bit will be for hour.
Max
No, no.
bit.
I mean the time which they have given.
Yeah, it looks like it should be in the hour range, right? Yeah.
Not sure. Okay.
Yeah,
Okay.
because see, in your
Yeah.
line 13,
Okay.
you look for that, right? And then that is actually added to your. And then, okay, you are actually forming all that and then you are validating on line 17. Okay.
Yeah.
Yeah, so the way I was saying, we can actually create a map of that. Okay.
Yeah.
So initially we can do a map saying, uh, okay, we run from the hours 1 to 12, okay, and for minutes 1 to 60, right? And in
Yeah.
that, for each and every number, what we take, okay, we will check how many bits it has, okay. So based on that, we'll form a key, okay. That key will be the number of bits, and then we'll push on the number of values into that uh, map key for that corresponding map key. So we'll have a list for a map key which will hold the values of hours and values of minutes, right? So then it becomes more easier, right? Instead of actually validating year in the Zulu.
Yeah.
Okay, maybe I'll share my solution,
Sure, sure, sure.
and then yeah, it is slightly similar to yours.
Yeah.
So this is the way it is. Okay, so what I'm doing here is, the way I was explaining, uh, just ignore this for now. So this is okay. No, we can't ignore. That is what it is. So these are the two maps. One is the hour map and the other is the minute map. So first I actually fill in the hour map. Okay. So what I do is I go run from 1 to 12. Okay, and then I count the number of bits. So this bit counts doesn't do anything much. It just looks at whatever the input is and gives you the number of bits in it. Okay, so I
Okay.
actually take that key in the map and push in whatever my values are for that particular bit. Okay, so I do the same thing for my minutes also, but I maintain two different maps. Okay, I'll quickly show what that bit count does. Okay, I think it is here. No, it was very above. Yeah. Okay, so it just goes in here and then keeps on removing the rightmost bit one at a time and then keeps the count of it, right? So the way we do for a bit counting most of the time, correct?
Yeah.
So that is what I do here. Okay, when I fill in these two maps, now I have the value stored for each and every bit, correct? So now the question is about this num. Okay, so num, if it is uh, greater than or equal to 3, okay, so then I do slightly different, because I know that I'll have to use the both hours and minutes. So first what I'm doing here is, okay, so I get whatever is the least which is in the part of the map for hours, I just store it here for my num is less than or equal to 3. Okay, so whatever my num value is, I just store here and then get the hours value. Okay, and then I form my answer. It's very straightforward. So I know very easily I can form an answer because my num fits with less than or equal to 3, and they are all the valued hours. So I take that vector or the list, whatever it is, and iterate through the whole list, and then I can just create it into an answer by converting into a string.
So one thing like the ternary operator which you have used, if hours is greater than 9, then you are using this one two
Well,
string
yeah.
same
So,
both
well,
are
actually,
different.
it's so I don't need to use that ternary operator. I can just use this. Okay. So that's not required. So I was trying something else.
Okay.
Okay. So this itself is sufficient for the hour. Okay. I can still optimize it much better. But if you look for minutes, okay, it is doing that here, because if I look for minutes, okay, if this is greater than 9, okay, so then I'll have to use a 0. I cannot use that number, right?
Yeah.
Okay. So that is what I'm doing here. So I'm just forming these two strings with the minutes and hours. That is one thing. But I can still have a combination of minutes and hour also, right? In this case, right? So
Yeah.
because my num, and then I'm actually using a while loop here. So I'm actually distributing my values between the count and num. Okay, so I'm actually increasing the count, setting the count to 1 first, and then decrementing my nums over here, and then going in the hour this loop again, because I know what my num is, and num represents the hours. So I take the hours list here, okay, and then when I come in this while loop, okay, so I actually have the hours. Okay, here also I have to change it.
Yeah.
Okay, yeah, so then I come here, so I know what my minutes counts are going to be. So the list of the minutes, right?
Yeah.
So I will get a list of all the minutes. Then I'm actually going to going to do the BFS sort of a graph way, right? So every time I combine the hour what I am at with current hour with the minutes, and then form an answer. So when I'm done with this, I increment my count. So I'm incrementing one more bit to my minutes and decrement my one more bit in the hour. So I keep doing this till my num is greater than 0.
Yeah.
Okay. So once that is done, I'll come out of it. So I'm done with this. So this part. Okay. When my num is greater than, less than or equal to 3. So, but if my num is greater than or equal to 3, okay, so greater than 3, not greater than equal to 3. So I'm using the last part only here, right? So what I'm trying to do is I'm taking count. In this count, what I'm doing is num minus 3 initially, and then I'm keeping my num to 3. And I'm doing exactly the same what we were doing earlier. For num, if it is greater than 0, I do follow this whole while loop. Okay. So then I get whatever the answer are. And then for the very last case, when my num is completely 0, I still have one bit, some of the counts, but they are only in the minutes part, right?
Yeah.
So then I have to actually include them also. So just I go through the minute, the list in the minute, and I actually add them to my answer. So I've just actually separated the whole solution into two different parts, right? Num is less than or equal to 0, or num is greater than, sorry, num is less than or equal to 3, okay, or num is greater than 3, okay,
Yeah. Yeah.
and that is the way I've separated. So this is a lengthy solution. I actually can club this, I think this might not be required. I can use the only last solution also, right?
Yeah.
But I think how I will handle this, then I'll have to handle the hours in a separate section. So I'll have to keep that. So to keep things simple, I made all this stuff, but I can modularize most of the stuff, right? So make the hours separately in a different model, in different function. Same for the minutes, right? Then I could combine it much easier. Yeah. So this was one solution, right? Yeah.
I don't know
So
why.
I actually use the number of set bits in hour and seconds. So
Okay.
the sum of the number of set bits in hours and number of set bits in seconds will be equal to nums.
Mm-hmm.
So we can use that concept to formulate the string.
Mm-hmm. Would you like to share it here?
Yeah, just
Yeah,
a
please.
moment. Okay, so this is the base case. Then since we know the total number of set bits will not exceed 10, like 1 2 3 4 5 6 7 8 9 10. So it will be almost equal to 10. So the possible value of nums will be from 0 to I guess 10, since we have only 10 number of set bits in the whole watch. So uh, first we know the set bits in 0, and when the hour is 0 or the second is 0. So I just pushed 0 and 0 0. Now for seconds, we know for seconds what I did was this built-in pop count calculates the number of set bits in an integer. So what this will do is it will make a map-like structure where all the numbers having same set bits will be clubbed together. Same I did for hours, and since it was mentioned that the uh, possibility of hour is from 0 to 11. So this loop is from 1 to 11 and 0 was handled here. Again, minutes will be from 0 to 59. So I coded for 1 to 59 and the 0th case was handled here. Now, uh, if the value of nums is, let's suppose 3. So we know that there can be only uh, four, four or five cases where we can divide the hour and seconds. Like for example, hours can be hours can take 3 set bits and seconds can take 0. Then hours can take 2 set bits and second can take 1. Similarly, uh, this will go to 1, S will be 2, and H will be 0, and S will be 3. So we need to form all the strings where the set bits in where the set bits is 3 and set bits is 0. This is the base case 0 0. Again for this one we need all the hours which all the values of hours which has set bits 2, and again all the values of seconds which has set bits 1. So for this, first I assign this to hour and second. Then in the map structure, I just pass this value, and then we need to just uh, construct all the combination of string.
Possibilities, yeah.
Yes. So,
Yep, that's
but
perfect. Yep.
What
just for
about
this,
minutes?
Yeah, he's saying second, but it's minute. Yeah.
Oh,
yes.
second is minute only.
Okay.
Yeah, that's fine. Yeah.
I just
It
Okay.
doesn't it doesn't have to be displayed, right? Yeah. Is
Okay.
the
yes.
internal voltage. Yeah.
So
Yeah, yeah, got.
just this case has to mention handled where the minutes is from 0 to 9. We need to add extra 0. So I just check the length of the in
Hmm.
Yeah.
minutes.
Yeah. This is a very concise solution, right? Yeah.
I just coded this now. I
Hmm.
was just fixing all the bugs, so it took time. But
Hmm.
I think this is very
Yeah, this is perfect. Yeah.
small solution to code it.
Yeah.
Concise one, yeah.
Yeah.
Yes, just we need to use the number of set bits, and also we could have used the map. I just used the vector of speed.
Yeah. Vector
Hmm.
works here. Absolutely.
Exactly.
Because for each and every vector index, that is going to be the number of bits, right?
Yes, it will be like
Yeah.
h of 0 will be uh, 0, then h of 1 will be a vector
Zero one.
again. Okay, so 1, then it will be 2, then it will be 4, then 8. Similarly,
Okay, first bit is set in all these cases.
no, the total number of set bits has been counted. So this built-in pop count counts the total number of set bits in the number. So the set bits in 1 is 1, in 2
Yeah,
it
yeah,
is
yeah,
1,
got
so
it,
it
got
is
it.
1.
Hmm.
So
number of
Two, it
set
will
bits.
be, yes. So again, this will be a list. So this now once we know that the number of set bits is either one or two, then we can construct all the possible uh, strings using this structure. Again, there will be another structure for the minutes. So we just need to do all the combinations of the both structures. So this is what happened here.
Yeah.
Yeah.
So yeah, at the corner case, you need to handle the what you did in the line 27.
Yes, since in minutes the values can be from 0 to 9, there we just need to append the 0 at first.
Yeah.
Beautiful. Yeah, very good.
All right, so I will just
Yeah.
stop share.
Yeah. Wow. Thank
Yeah.
you.
That's awesome. Yeah.
Yeah. Cool.